Hello everyone, I am Sukanta, a participant of the refresher course on Astronomy and Astrophysics 2021, organized online by Inter-University Center for Astronomy and Astrophysics, Pune, from May 10 to June 11. My group is Cosmology group. On behalf of the following members of the group, I will present a topic, namely standard candle, the beacon of the universe. So I am going to talk about type 1 or classical Cepheid and type 1 is supernova, denoted by SNE1A. This figure shows a candle having a fixed luminosity placed at different distances in space. The candle appears fainter at greater distances. How faint it appears tells us about its distance in space. Now the question is, what are standard candles? Any distinguishable class of astronomical objects of known intrinsic luminosities that can be identified over a wide range of distances is called a standard candle. For measuring distance to a remote galaxy beyond Milky Way, astronomers always look for a standard candle. By using their intrinsic luminosity, expressed in terms of absolute magnitude, and measuring their apparent brightness or flux, expressed in terms of apparent magnitude with a telescope, their distances and hence the distance to the host galaxy can be determined using the distance modulus relation given by mu is equal to 5 into log of d by 10%. And this gives distance in parsec is equal to 10 to the power 0.2 mu plus 1, where mu is equal to small m minus capital M, called the distance modulus. Here small m is the apparent magnitude corrected for extinction, and capital M is the absolute magnitude. Extinction refers to the loss of stellar light due to absorption and scattering, and this apparent mean magnitude has to be corrected for extinction before we use them for distance determination. This figure shows that if we know the luminosity of a certain type of celestial object, then by observing its apparent brightness, we can calculate its distance. Now, what makes a standard candle? For an astronomical object to be a standard candle, it should be luminous enough to be seen at great distances, and we should be fairly certain about their luminosities. They should be easily identifiable, for example, by the shape of the light curve of a variable star or a type 1a supernova, and they should be relatively common, so that astronomers can use them to determine distances to many different galaxies. How to obtain intrinsic luminosity of a star? Distances to some of the nearby objects are determined using parallax method or other direct methods, and apparent magnitudes of the same objects are obtained from telescopic observations, where apparent magnitudes are denoted by m lambda, and the values of absolute magnitudes are determined using the distance modulus relationship, where absolute magnitude is denoted by m capital M lambda. Then a relationship can be constructed between the absolute magnitude or intrinsic luminosity and the simpler observable quantities, such as the period in case of variable star, that is capital M lambda is equal to is a function of sub observable parameter in a photometric band lambda. This relationship is known as a calibration relation, and it allows us to determine distances. Now this apparent magnitude is corrected for extinction using the relation m lambda is equal to m lambda minus a lambda, where a lambda is the extinction, and this is equal to r lambda into e b minus b. So where r lambda is basically all the ratio of total to selective absorptions, and for a reddening law, it is held fixed for a particular wavelength band, and E of b minus b is called the reddening, and it is obtained from the reddening map or from the multicolor photometry of variable stars. So we are going to discuss about the widely used standard candles, namely the type 1 or classical Cepheid and type 1a supernova. So type 1 classical Cepheids are radially pulsating young population 1 variable stars which pulsate due to an intrinsic mechanism called the Kappa mechanism. On the other hand, type 1a supernova is an explosion resulting from the thermonuclear runaway of a white dwarf star with mass greater than the geometrical limit, which is in a closed binary orbit with a large companion star, where geometrical limit is given by 1.44 times the solar mass. Now let us talk about type 1 and type 1 or classical Cepheid in details. So they are the radially pulsating yellow supergiants, and these stars have left the main sequence and are in a post core hydrogen burning and core helium burning. They have typical masses in the range 4 to 20 solar masses and can have luminosities up to 10 to the 5 solar luminosity. And because of their high luminosities, they can be used to measure distances up to 35 megaparsec. They are population 1 star, that means they are very young stars with an age greater than or equal to 300 million year, with periods between 1 to 200 days, and their temperatures range from 6000 to 8000 degree Kelvin. They obey a well-defined paired luminosity relationship given by Leavitt law, and lambda is equal to A lambda plus B lambda into log P, where lambda is absolute magnitude in a photometric band lambda, and P is the period of a CFIT, and A lambda and B lambda are basically the intercepts and the slopes of the period relationship, and this is obtained from the galactic CFIT calibration. So Leavitt law states that the longer the pulsation period of the CFIT, the more luminous the star is, and this shows figure shows the HR diagram of stars, and type 1 classical CFITs they're shown here within a strip or the instrumental strip, and there are other stars also like RLA stars, and type 2 CFITs are also there within the instrumental strips, but their absolute magnitudes are quite small as compared to type 1 classical CFIT. And all the stars within the instrumental strip, they pulsate when they enter into the instability strip. And this is basically an animation showing the pulsation of a CFIT. You can see that the star radially goes in and out, and that means that its layer expands and contracts due to a mechanism called the kappa mechanism, and due to this contraction and expansion in a regular manner, there is also a variation in the luminosity as a function of time. So which can be plotted in a graph. You can see, and this graph is known as the light curve of a variable star, where we have plotted the time along the x-axis and the brightness along the y-axis, and from the light curve we can find out the period of the CFIT. Now this is an example of a CFIT taken from the optical gravitational lensing experiment project. This CFIT belongs to the Large Magellanic Cloud, to one of the satellite galaxies of the Milky Way, and this is a period of the order of k is equal to 5.61, and then T naught, it is a epoch of maximum brightness, and this is given as rho 171.780 for the star, and this A naught is obtained from the Fourier fit to the phase light curve of the star, where the phase light curve is obtained by using this relationship phi is equal to T minus T naught by capital P minus integer part of T minus T naught by P, where P is obtained from the time series, or from the time series or the light curve of the variable star, and T naught is also obtained from the time series of the variable star. And now this A naught is basically it is the mean magnitude of the star, and whenever we construct a PL relationship, then we use this mean magnitude. This is the mean magnitude. This A naught is basically the mean magnitude, and this is given by this DC line. This is line. So this DC line basically tells us about the mean value, about the mean magnitude of the variable star. And we plot, whenever we plot a PL relationship, so we plot P along the x-axis, and this apparent magnitude or absolute magnitude along the y-axis. And this apparent magnitude is nothing but this A naught term of the Fourier series expansion. Now let us discuss about the classification of type 1 CFITs. Type 1 CFITs are classified into three classes: fundamental mode CFITs, first order CFITs, and second order CFITs. First order CFITs have quite a symmetric light curve, and they have higher amplitudes, and their period goes from 1 to 200 days. On the other hand, first order CFITs have smaller amplitudes, and their light curves are somewhat symmetric, and the periods goes from 1 to 10 days. On the other hand, second Overton CFITs have nearly sinusoidal light curves with very small amplitudes. Amplitudes are less than 0.1 mag, and they have periods less than 1 day. This figure shows the Leavitt law, in which the luminosity of the star increases as the period increases. And this CFIT can be basically used to determine distances to nearby galaxies. So this is basically the absolute magnitude of the CFITs in our own galaxy, and this blue data points show the galaxies observed in some other galaxy, which we call it as a target galaxy, and these are nothing but the apparent magnitudes. And so if we just take this line, if we take this m is equal to a plus b log p, downward to match the data points of the observed galaxy, then that vertical offset is basically tells us the distance modulus of this target galaxy with respect to this to the galaxy, to our galaxy, or to with respect to the Milky Way galaxy. Now, what we do is we study about this type 1a supernova. So type 1a supernova, also denoted by SNE1A. So a white dwarf in a closed binary orbit with a large companion star is likely to accrete matter steadily from its companion, which is shown in the left hand side of this figure. At some point of time, the infalling matter raises the white dwarf's mass to above the threshold of the Sreekala limit, given by 1.44 times the solar mass, and the core then becomes gravitationally unstable and implodes, and giving birth to a type 1a supernova. And sometimes both the stars in the binary may evolve into a white dwarf without any mass transfer, as shown in the right hand side. And the pair of white dwarfs emit gravitational waves, as these white dwarfs are very compact objects, so they emit gravitational waves, and as they orbit each other, and resulting in the loss of orbital energy and decay of orbital separation. And eventually the two white dwarfs will spiral and merge, producing a super Chandrasekhar mass white dwarf that immediately collapses and explodes as a supernova explosions. Now the supernova type 1a have absolute magnitudes of the order of minus 19.3 mag, and in terms of luminosities, their luminosities are very high, 10 to the power 10, and hence they can outshine the entire hot galaxy before fading away. And since their luminosities are very high, so they can be used to prove much further into the universe. So this is an example of a supernova SN 1994. Which is observed in a galaxy. The image is taken from the Hubble Space Telescope. Now, formation of type 1a supernova. So, due to the sudden decrease in the gravitational potential energy as the core collapses rapidly to a smaller radius, a huge amount of energy is released that blows the star apart. So, energy release is given by GEMC square divided by RC, and this comes out to be of the order of 10 to the 53 arcs. For a core mass equal to the Sreekala limit and core radius equal to 10 km. Now I show here I show the movie of the formation of a type 1a supernova from a binary system consisting of a white dwarf and a large companion star. Sorry. So this movie shows a white dwarf, and and this is a large companion star, and the white dwarf is accreting matter, and it becomes unstable and basically implodes as a type 1a supernova. Classification of supernova. Supernova are classified into different classes. So here we are talking about type 1a supernova. So type 1a supernova, it does not contain hydrogen lines, but they have a silicon absorption feature at around 615 Armstrongs. And there are other supernova which are classified based on different spectral lines. And here we can see that this silicon lines absorption feature is quite evident in the type 1a supernova spectra. And depending on the type of the supernova, there are different absorption features occurring in the spectrum. So how we can use supernova type 1a as a standard candle? Supernova type 1a are the most luminous of all supernova, and hence they can be seen at very large distances. They exhibit a great uniformity both in their spectra as well as in their light curves. And their spectra contains no hydrogen lines but a silicon absorption feature at around 6150 Armstrong. And their light curves show that their luminosity varies rapidly as a function of time to reach a peak value, followed by a gradual decline over a period of 30 to 40 days, in which more luminous objects have slower decline rates, and this simple behavior allows them to be calibrated as standard candles. So this figure shows the light curves of supernova, and I can see that how uniform they are. And these supernovas are characterized by delta M15, which I am going to discuss. And you can see that luminous supernova have a lower value of delta M15. These are the values of delta M15. Whereas fainter supernova have higher values of delta M15. And this B, V, RI are the different photometric bands. So the light curves are quite uniform. On the other hand, the spectra also, they are also uniform. So the spectra of different supernova are quite uniform. So the use of supernovas as standard candles is based on the assumption that all the white dwarf progenitors will approximately have the same mass equal to the Sreekala limit, and consequently the same exposure energy and luminosity. A small degree of radiation may reflect the differences in accretion rates, rotational velocities, and carbon to oxygen ratios. The absolute magnitude of type 1 supernova are almost constant in the V and V band, and given by MV is equal to MV equal to approximately equal to minus 19.3 plus minus 0.03 mag. Now we have seen that the luminous supernova have slower light curves, and in other words, the more slowly the brightness decreases, the more luminous the supernova is, and there are various ways of quantifying this effect. And so, irrespective of the progenitor mass, it can be shown that the maximum luminosity of a supernova is given by this relationship, and this is known as the Pareto relationship. And here delta M15, basically it refers to the magnitude difference between the maximum light and 15 days after. So if you are observing the supernova in the B band, so this will be delta M15B, and since this is a relationship in the B band, so there are other relationships also in other bands. So return study equals to just refer to this paper by Pareto et al. 2006. And you can see that this is the figure of a typical supernova light curve, and you can see this is the maximum brightness. We take this as the 0 day, and the 15 days after 15 days is the 15 days from the maximum brightness, and this width is basically delta M15. And since this is the B band, and therefore we use a delta M15B. And so therefore the width of the light curve peak is correlated to the peak luminosity, and therefore the brighter or luminous type 1 supernova have broader widths, and therefore higher absolute value corresponds to a smaller delta M15. So luminous type 1 supernova fades slowly, and less luminous supernova type 1 fades very fast. After correcting for this width luminosity relationship, the light curves agree remarkably well and reach about the same magnitudes, and hence can be used as standard candles. And here is an example of a supernova SN2011 FE observed in the galaxy M101, which is also known as the Pune galaxy. And the observed peak brightness is 10, and this delta M15 is 1.21. And this therefore absolute magnitude can be obtained from the relationship that we have just discussed, and this gives MV is equal to minus 19.255, and therefore we can find out the distance modulus, which is the difference between the apparent magnitude and the absolute magnitude, and this comes out to be 29.255. And next, using this relationship, this is in megaparsec. This is distance modulus in megaparsec, and using this relationship, we can find out that the distance is equal to 10 to the power 0.2 mu minus 5, and if we put the value here for mu, which is equal to 29.255, then we find that the distance to the galaxy is 7.096 megaparsec. And the data of this supernova is taken from the Richmond et al. 2012. Now let us discuss distance ladder, and this is a way by which we can measure far off distances. So distance ladder refers to the steps making possible for the measurements of progressively larger distances. It is called a ladder because measuring distances to the closest objects requires one technique, while those of the more distant objects require another technique, and that relies on the first technique, and so on. So the various methods of distance determination are thus interrelated because one is used to calibrate the other. So we will try to see how the Hubble constant can be measured using distance data. So astronomers use cosmic distance data to measure accurate distances to nearby galaxies and galaxies which are very far away from the Earth using the following few steps. First step is basically called the galaxy fit calibrations. So this step also contains a number of sub-steps. And first of all, measurement of distances to a number of Cepheids in our own galaxy using parallax method. And this parallax can be obtained from the Gaia missions or from the Hipparcos missions. And Gaia has provided the parallaxes for a large number of Cepheids in our galaxy, and therefore those can be used to find the distances. And then the same Cepheids are also observed, and from the observed light curves we can find the apparent magnitude and the persistent periods. And then since the distance and apparent magnitudes are known, so therefore we can find out the absolute magnitude. And since the absolute magnitude and the period are known, therefore they can be plotted in a graph and fitted with the function of the form m is equal to a plus b log p. This of course depends on the wavelength band. I have not given the subscript here lambda. So, but this relationship is basically wavelength dependent. And this E and B are obtained from the least square fit, and this is called the galaxy Cepheid calibration. And this relation can be used to find the absolute magnitude of any Cepheid with a period p in any galaxy. And step 2 is basically called the distance measurement to nearby galaxies, and which host both the Cepheids as well as one or more type 1a supernova. So we consider a galaxy, we observe a galaxy which hosts a large number of Cepheids and one or more type 1a supernova. From the observed light curves of these Cepheids, their apparent mean magnitudes and the periods are determined. And then using equation 3, the absolute magnitude for each of the Cepheids are determined. Finally, the distances to each of the Cepheids are calculated using equation 1, and that means the distance modulus relationship, and has the distance to the host galaxy. In this way, galaxies to a large number of Cepheid host galaxies are obtained, which also host type 1a supernova. And since the Cepheids and the type 1a supernova belong to the same galaxy, they will have the same distance modulus, and the true brightness or absolute magnitude of the supernova in each of the host galaxies can be measured. This is called type 1a supernova calibration. Now, once we calibrate the supernova, then we use them to determine distances to far-off galaxies. Now, we look for supernova in far-off galaxies from the Earth, and unlike Cepheids, type 1a supernova are bright enough to be seen at relatively longer distances. And comparing the absolute magnitude and the apparent magnitude of distant supernova, we can measure out to the distance, but the expansion of the universe can be seen. And comparing these distance measurements with the redshifts, which denotes how the light from the supernova is stretched to longer wavelengths by the expansion of the universe, we can calculate how fast the universe expands with time, called the Hubble constant. The above 3 steps are schematically depicted in the following figure. And so these are the 3 steps by which one can basically calculate the Hubble constant. And using these 3 steps, Rees et al. 2018 obtained the value of the Hubble constant equal to 73.53 plus minus 1.62 km per second per megaparsec. Now, the type 1a supernova can also be used to study the accelerated expansion of the universe, and a plot of lightning corrected distance modulus of the type 1a supernova and its residual velocity, as tracked by the redshift determined from its spectrum, is known as the Hubble diagram. And the diagram can be compared to the predictions made from the cosmology with specific values of the matter density given by lambda, given by omega m, and dark energy density omega lambda, and the dark energy equation of state parameter omega. Now you can see that higher redshifts are observed supernova, type 1a supernova are significantly fainter than is expected from the luminosity distance relationship, which implies that the universe is accelerating, and that means a double dot is greater than 0, where a is known as the scale factor of the universe, and invoking a 30% energy density in non-relativistic matter and 70% energy density in dark energy, also known as vacuum energy, fits the data well with a flat universe given by k is equal to 0. So now you can see that using this, similarly for from the high Z supernova search team, they also obtained the same thing at lower redshifts. The data can be fed with all the 3 cosmological models. But as you can see that cosmological models with with a matter density equal to 0.3, and this dark energy density 0.7. It fits the data very well, and for other two values, the data this fits deviate a lot from the data. So now this dark energy, you can see that it contains around 70% of the energy density of the universe, and this dark energy has a very as a exotic property that it has a negative pressure, which implies that the internal energy grows while expanding, and if the expansion is expected is considered to be an adiabatic expansion. Now it is in contrast to what is known from the first law of thermodynamics, is that in an adiabatic expansion, the internal energy density decreases as the gas has to perform work done against the surrounding to grow in volume. It is such a counterintuitive property that leads to cosmic expansion or cosmic antigravity at large distances. And these three scientists, Professor Saul Perlmutter, Professor Brian Smith, and Professor Adam Rees, were awarded Nobel Prize in Physics 2011 for the discovery of the accelerating expansion of the universe through observations of distance type 1a supernova. Thank you very much for your kind attention.